All right, let's dive right in. Today we are heading to the absolute cutting edge of physics. And I mean, forget what you learned in your high school textbook, we're exploring 3 brand new breakthroughs that are shaking up everything scientists thought they knew about the fundamental nature of reality itself.
So, think about it. Quantum mechanics has been around for more than 100 years. It's the magic behind our computers, our lasers, pretty much all modern technology. You'd think we'd have it all sorted out by now, right? Well, not even close. The truth is, the deeper we dig, the stranger things get. The frontier of physics is still just packed with these profound, unsolved mysteries.
And in this explainer, we're going to tackle 3 of quantum's biggest puzzles head-on. Now, these aren't just abstract thought experiments. These are areas where scientists are making real progress with some incredible new discoveries. We're going to start with a really bizarre paradox, then move on to decoding a secret language of nature, and finally, we'll ask the biggest question of all: what even is reality?
Okay, first up, we have a paradox that sounds like it just completely breaks all the rules of thermodynamics. You might have heard this weird fact that hot water can, under certain conditions, actually freeze faster than cold water. It sounds impossible, but it's a real thing. Well, it turns out physicists have found a quantum version of it, and believe me, it's even weirder.
It's called the quantum Mpemba effect, or QME for short, and the idea is just wild. A hotter, more energetic quantum system can sometimes cool down and reach its stable, cold state way faster than a colder one. I know, it's totally counterintuitive. It goes against everything we think we know about heating and cooling, but it is a real observed effect.
So, to make it simple, the classic example is hot water freezing faster than cold. The quantum version? It's the exact same principle, just happening at the tiniest microscopic scales. In both cases, you have the same central mystery. How on earth can starting from a higher energy state actually be a shortcut to getting to the lowest one?
So what's the big new discovery here? Well, scientists found that this whole effect gets supercharged when a material is right at a tipping point. I mean, right on the very edge of changing its fundamental properties like its magnetic state. They call this a quantum critical point, and that, it turns out, is where all the really interesting stuff happens.
Think of it like this. Usually, a system kind of takes its time to cool down and relax, But when you push it to that critical point, it's like it discovers this incredible shortcut. The universe suddenly opens up an express lane, and the system can just zoom down to its final state almost instantly. It's a massive difference.
Okay, so why should we care about this? Well, on a practical level, if we can learn to harness this effect, it could be a game changer. We're talking about a powerful new tool that could lead to faster quantum computers or other wild technologies. But even more fundamentally, it deepens our understanding of one of the most basic processes in nature, how anything, from your morning coffee to a single atom, finds its balance.
Now, for our second mystery, we're shifting gears to talk about decoding nature's fundamental rulebook. Imagine you're in a pitch-black room and you hear a bell ring. Just from that sound, could you figure out its exact shape, what it's made of, its size? That's kind of the heart of this incredible challenge in physics called inverse quantum scattering.
You see, for decades, physicists have been trying to solve exactly this kind of problem. They smash particles together in giant accelerators, and then they study all the debris that comes flying out. From that data, they have to work backwards to figure out the fundamental forces, the actual blueprint that govern that collision. And until just now, the math to do that was, frankly, a complex, multi-step nightmare.
Right. So the old way was this clunky 3-step process. You had to build a model, then add some stuff, then combine it and refine it over and over. But the breakthrough is a single, incredibly elegant mathematical tool that does the whole job in one go. It's called the Unified Wronskian Formula, and you can think of it like a master key that just unlocks the final answer directly, instead of fumbling around with 3 different keys.
The impact of this is absolutely huge for the physicists doing this foundational work. This new formula gives them a much faster, more precise, and more rigorous way to reconstruct the forces happening inside the nucleus of an atom. In short, it's a much sharper tool for decoding the secret language of the universe.
And that brings us to our final mystery. And honestly, this is the deepest, most philosophical one of them all: the measurement problem. This isn't just about how things work, it's about why reality itself looks the way it does. Why isn't everything just a fuzzy quantum blur all the time?
So here's the central question, the real head-scratcher. A quantum particle, like an electron, can be in many places at once. It's in a superposition of possibilities. A good way to think about it is like a spinning coin that is somehow both heads and tails at the same time.
But the moment we look at it, it instantly collapses into just one state. It becomes either heads or tails. Why? What's so special about the act of looking?
The standard view has always been kind of unsatisfying. It basically just says, well, collapse happens when we observe something. But a bold new idea, called collapse models, proposes something completely radical. It suggests that our observation doesn't create the collapse. Nope. Instead, collapse is a natural, ongoing process, and our act of looking just reveals a collapse that was going to happen anyway.
These models suggest that tiny, random collapses are happening constantly, everywhere in the universe. Now, for a single particle, the effect is so small it's basically negligible. But for a big object made of trillions and trillions of particles, like a cat or a planet or you, all those tiny effects add up and force the object into a single, definite state. This just elegantly explains why the world we see looks solid and classical. And the best part? It's actually testable. Experiments are happening right now to see if it's true.
So let's just take a step back and pull all of this together. We've just looked at 3 incredible advances happening on 3 very different fronts of quantum physics. So what does this all tell us about where the field is heading?
What we're really seeing here is progress happening on every single level. We're finding out that quantum systems behave in even stranger ways than we imagined. We're forging sharper, more elegant mathematical tools to make sense of the data we're getting, and we're proposing bold, testable new theories to answer the biggest, most fundamental questions about reality itself. It's an amazing time.
And this leaves us with a really fascinating final thought. We've got a new physical effect, a new mathematical formula, and a whole new theory of reality. Each one is a serious contender to completely change our understanding of the universe. So the only question left is, which one is going to be the first to rewrite the textbooks of the future?
For more explainers like this one, you can reach out to us at www.multigan.in. And of course, don't forget to like this and subscribe to the Multigan YouTube channel. Thanks for watching.